So far we've been talking about the theory behind Bayesian models and how to think like a Bayesian. And then we've been fitting models with the R package BRMS. So now we're going to talk more about Stan itself and how you can code a custom Stan model. So this here is a complete Stan linear regression model. And every Stan model you look at is really going to have these same types of sections. So we've got a data section, we've got a parameter section, and we've got a model section. In our data section, we define things that come in as a list from R. And these can be things like integers or reals or vectors. So real is continuous value, integer is a whole number value. We can declare lower and upper bounds on those. So here I've said that my number of observations has to be at least 1. I don't have to write that in, but that's just trying to protect myself from doing something silly in the future. Then I declare that I've got a response vector of y and a predictor of x, and that's what they're named in my list in R, and I'm telling Stan that they are of length n, which it needs to know. I define my slope parameter I'm going to call beta, my alpha parameter which is my intercept, and sigma, which is my standard deviation on the observation error. And importantly, I tell it that it has a lower bound of 0, and then this implicitly Stan will treat this as only having support above 0, and therefore the priors will also be half priors as defined below. So my sigma student t is actually a half student t with a degrees of freedom of 3, a mean of 0, and a scale parameter of 2. And then I've got a normal 0,10 prior on my intercept, and a normal 0,2 prior on beta. And then I've got my data likelihood, and there I've got my response y, which is sampled from a normal density, kind of the equivalent of d norm in R that you've seen before. Alpha the intercept plus my predictor x times my slope, observation error sigma. All of my lines have a semicolon after them because it's inspired sort of by C++ syntax. So that's a complete model. And let's break this down. So that lower is not strictly necessary, but good practice. If you have bounds, you could try to protect yourself or others using your models. Semicolons are necessary. You will get errors if you don't have them. You will forget them. And you need to define dimensions of vectors and matrices and arrays. And we've been through this here. So you've got the priors, you've got the data likelihood. You can break things across lines like I've done there here with that y tilde normal line. There are other optional sections. So you can also have a transform data section. You can have a transform parameter section. You can have a generated quantity section. So let's talk about those different sections. So the transform parameter data section is optional. And this is just taking the data that you input and manipulating it in some way before you fit your model. Sometimes it just happens to be more convenient or faster because it ends up being compiled C++ code to do computations in Stan. But there's no reason you couldn't do it in R beforehand. And it's done once before fitting, so it doesn't really have a big impact on the fitting speed. Transform parameter section, optional again. It creates transform to derived values to use in the model section, which you could also do in the model section itself. But the important thing is that things that you do within your transform parameter section get recorded by the MCMC sampler as transformed parameters. So you can look at the samples from them. And it's done on every MCMC iteration. The generated quantity section comes at the end. It's optional again. It usually is a convenience. These are things that you want to do with the parameters and transform parameters of your model to generate things that you want to look at the MCMC samples from. You could always do that afterwards in R, and we'll show an example of doing it after in R versus doing it in Stan itself. Usually it's just a convenience. But there's some times when it is essential. For example, if you're using some kind of like a math library function that's built into Stan that isn't written in R. It's done once after MCMC is finished, so again, it's relatively fast. Common uses would be things like posterior or prior predictive simulation. We'll look at that. Calculating log likelihoods for expected log predictive density calculations within the leave1out-r package. We're going to look at that as well. Mostly doing things in the generated quantity section is a convenience because you already have the parameters and data set up in a structure where it's easy just to write this section versus having to do all the data processing yourself again in the output. We'll see how that gets more complicated if you do it in R yourself. I'm going to move my face. So this is an example of doing posterior predictive simulations in our simple linear regression. So I've added a generated quantities section at the bottom. I've defined an array here, and it's of type real. And then I say the thing that I want to save, which is the y_rep, or replicates of y. There's a whole family of random number generating functions that usually look the same as the density function with _RNG. So here in normal _RNG. And then I'm going to recreate my expectation. So my intercept plus my slope times my predictor, adding on the observation error. And that is going to create a one-dimensional array here of replicates of my posterior predictive simulations. I could have done that myself using rnorm in R, and we'll see an example of that. I also think you could probably use this as a vector. I don't think it matters here whether it's a vector or an array. Prior predictive simulations, not that different than the posterior predictive simulations, other than we need some way to tell Stan whether or not we want to include the data likelihood. I think we saw this when I poked into the code for the BRMS model. Here we're going to do it ourselves. So the trick is that although there are not true and false object types within Stan, there are integers, and Stan will treat a 0 versus 1 as a true false. So if you create an integer here, something I'm calling prior only, and I'm saying it has a lower value of 0 and upper value of 1, it now only has two possible states. And then I use the exclamation mark syntax to say, if that is false, then include the data likelihood. If it's true, do not. So if prior only is true, we do not include the data at all. We only sample from the priors. And then we do something similar here in the generated quantities. And here I'm showing an example with the vector array would have worked as well. The vector is useful in some math functions that you might use within the model section. It doesn't matter here whether we use an array or a vector in the generated quantities. And here's also, there's a difference between what I did here, and they're both totally valid, and there's probably no difference in terms of performance in the generated quantity section. Here it's a vectorized statement. So we're not looping over the elements of yrep, but it works on the vector of x and the vector of yrep at the same time. Here I am looping using a for loop, same syntax as in R. So I, from 1 to the number of elements of my vector, one by one I'm going through my expected values, assuming I've saved those above, in something called mu, using the random normal generator to generate ysim. And we would do something similar for these pointwise log likelihoods, which may not make a lot of sense yet, but we'll talk about this after. But this is the same as dnorm in R, this normal underscore log posterior density function. And they all take this type of syntax. So the response here, conditional on vertical bar, the mean, and the standard deviation. That is part of my model. And again, here I'm looping over it, storing it in a vector that I call log_like. And as we'll see, that's because that's sort of a special name that is assumed by the LU package for doing calculations with these log likelihoods for model comparison. And we'll talk about that later. So I mentioned this briefly. I showed you two examples here. There's going to show you a vectorized and a looped version. And in the generated quantities, it doesn't matter. Whatever's easier for you, you can do. But in the model section, it does matter. So anywhere where you're sampling from a density function within your model, usually in the data likelihood, the vectorized statement is much more efficient due to how it calculates the gradients internally while running the no U-turn sampler. So if we use the looped version, this will take a lot longer. Vectorized will go a lot faster. So the key part here is that in the model section of a stand model, if at all possible, you want to use the vectorized format. So you don't want to be looping over the data likelihood. There are cases where you have to, for example, in some time series models, where things depend on the previous time step, for example. Often there's no easy way to vectorize it, and so you've just got to loop it. But if at all possible you want to vectorize it, it will be a faster model. And for a simple linear regression like this, it probably doesn't make any real difference. But if you get into models that are realistic complexity that take a while to fit, it can make a difference. Are there any questions on that? So again, we're now going to actually look at this same stand code. So we're going to come back to this right now. Okay. So I'm going to go into the Bayes course. This is from that GitHub repository. Exercise files, if you ran the code to generate the exercise files folder. Otherwise, just in the base folder, you'll find the same files with the answers already in them. And stand programming basic is where we're going to go through this. Okay, so in the first chunk, probably the only thing of interest is that I've created a little function here. And this function just is used to spit out the stand code when this R markdown file is compiled. So not something you would commonly do, but just explaining why that's there. So probably this is a good time to do a bit of an aside that there are two, well, there's more than two, but if you're working with R, there are two common ways to interact with stand. There's also a Python stand, and there's a command line stand. And within R, there's the original R stand, which is kind of the big behemoth package that most people use. It's on CRAN. But because R stand has to incorporate all of the stand code and a whole bunch of C++ headers, it often gets quite outdated from stand itself. So there's stand, and there's all these interfaces. And command stand is the closest to stand. It just runs on the command line. And so at times, R stand has gotten quite far out of date. And there is a lighter weight R package called command stand R, maintained by the stand folks. I don't think it's on CRAN, but if you click on this link, you'll see everything to know about command stand R. There is a way you can install it here, so it's already compiled, even though it's not from CRAN itself. And what this does is it lets R interact with command stand in the background. So when you first install it and load it, it's going to prompt you to install command stand R and link the two together for you. It's an extra step, but it's an option. It's got some reading and writing functions so that basically everything after behaves the same as with RStan, but it lets you use the latest version of Stan, and it's just a lighter weight package. So often I would actually use that myself, but here we're going to use RStan, which is more common for sure, and most of the code you see online is going to be with RStan. And for the most part, you don't need to be on the bleeding edge of Stan, so it's totally fine to be using a version of Stan that's a little bit old. So we're going to load RStan. And we looked at this before, but it's always going to give you this message when you first load RStan, which has some helpful information in it that you might want to put at the top of a script if you are working on a Stan model. So for example, this, if you copy and paste this, then your chains will sample in parallel. If you copy and paste this, then it sets RStan options so that it doesn't recompile your Stan model if nothing has changed about it. And then it gives you some information about within chain parallel processing, which you have to code explicitly in your model, We're not going to talk about that. That's certainly more advanced, something you don't see very often. It's a newer advancement in STAN. But parallel processing across chains is simple, straightforward. And for a model of moderate complexity, it certainly makes sense to be sampling in parallel. We're not going to do that because the models we're looking at here are quite fast to fit and will actually be slower in parallel. So we're going to use the default, which is just one core. This is that line of code to keep the model from having to recompile if nothing has changed. And again, we're going to simulate some really simple data. It's a linear regression here, setting our seed so that the random numbers are the same every time. 30 data points, a predictor, an intercept, a slope, observation error, generate our response, generate a data frame. Tybal's just a tidyverse version of a data frame. So we have X and we have Y. Looks something like this. So now we have a STAN model, and this is what we were just looking at in the slides. I'm going to hop over to the model itself in RStudio, so it's got some syntax highlighting, and we'll look at it again. Control.lm simple, or you can navigate to STAN lm simple. And so if you're using RStudio, it does have syntax highlighting built in. Also, if I source it, so Command-Shift-S, I think Control-Shift-S in Windows, RStudio will tell you whether your model is syntactically correct, which is quite useful because you will make all sorts of mistakes. So if I took off a semicolon, for example, and I sourced it again in RStudio, I get this error message, which in this case is fairly helpful. It says that you're probably missing a semicolon. So it does that without compiling the model, which saves you lots of time. So this is what we saw in the slides. We've got our data section, we've got our parameters section, and we've got our model section. And this is one of the things I really like about STAN, is that because you always have this structure and it's in this structure with these names, it's really easy to step into someone else's STAN model and figure out what's going on, as opposed to something like JAGS, where it can be hard to figure out what's data, what's a parameter, what's a prior, what's the likelihood. It's all just kind of mixed together. So you get these three sections, they're always named, they're always in the same order. And because RStudio also has functionality for STAN built in, as I was writing this, you would get auto-completion with everything that matches what you're typing. So it can be quite helpful for writing your models. So I'm going to go back to my RMD file, and we're going to set up the data to input into our model. So we're going to have to create a list that has a named list in R that has elements for N, Y, and X that we're going to pass in as data. And then the things that we get out of it are going to be named based on how we have named our parameters and anything else we had, like generated quantities and so on. But we don't have any of that here. It's a really simple model. So if we look at a slightly more complicated one, again, I'm going to do control.lm.stan. That's in the STAN folder in the root folder. This is the same as what we saw before, but I've added the generated quantities, and that's to generate some things that we're going to want to look at as soon as we fit our model. So we could have fitted without this, but we wouldn't have been able to do our posterior predictions or model comparison without some extra work in R ourselves. So instead, we're going to do it within STAN. So we just write generated quantities, create our braces here. We declare that we're going to have posterior predictions and something called log-like for the point-wise log likelihood. Point-wise just means it's observation by observation. So we have these two things. They are vectors of the same length as X and Y, and was declared in our data list. And then we're going to loop from 1 to n. And I will drag this over. And because we haven't saved what this means, we could have saved this into something in our transform parameters. We'll see that later. We're just going to recreate our expectation. So that's our mean. And that's our observation standard deviation. And we use the normal RNG so that we are simulating a new observation from a normal distribution. And then we also save our normal Gaussian density for our observation given our expectation, our mean, and our level of observation error standard deviation. So that is our pointwise log likelihood. We're not going to use that here. We are going to use that soon. That is so that we can use the leave one out, the LU-R package for model comparison, similarly to how you might use AIC for a regular maximum likelihood GLM or linear regression or model. So is there any questions there? We're going to come back and fit it now after this. Okay, I'm going to close that, close my simple file. So to fit our model, the simplest way to fit a Stan model with Stan, there are actually several ways, but the simplest way is to use the Stan function in the rstan package. So that function is within rstan. You don't need to write that because we've loaded the rstan library. We need to give it a path to our Stan file. Here I'm using the here package just because this is within our markdown file, and that forces to find the root of the folder, which is our Bayes course folder. You wouldn't necessarily need that ordinarily, but this is an RMD file. I'm trying to make it work for everybody. So that's the location of our Stan file. We tell it how many chains we want, how many iterations. Those are the defaults. We tell it the random seed. This is not essential, but this forces the MCMC sampling to use the same initial stochastic seed value. So the MCMC samples are the same each time, so that it's fully reproducible. And then probably the most interesting part here is that we have to declare our data. So we have to do that as a named list, as we said, and the syntax in R for a named list is just the list function followed by the name and then the contents of that named element. So if I do list x equals that, I end up with a list with a name x with the contents of my column x in the data frame dat. So I created a named list with x, y, and then the length of y, could have done the length of x, be the same thing, and I get this. Often, here this is really simple, so I'm doing it in the same line as my Stan call. Realistically, for more complicated models, I might do something like this. Create some kind of a named list outside of it, and then pass it in like that. That's the exact same thing. So I'm going to run that. Because you haven't run it before, you're going to have to wait 30 seconds or so for it to compile the C++ code for the model. Once it's compiled, it samples. Because we have it running in serial, not in parallel, it does one chain, then the other chain, then the other chain. And so now we have fit our first Stan model. Let me try and scroll back to where I was in this zoomed in window. So if we just call the name of the object, which is the same in R as print. So if we print our model, we get this output here on the right. So you'll see all the things that were generated quantities are being reported, which is making it kind of hard to read. So we'll fix that in a minute. But the first things it reports are our parameters, which in this case is our beta, alpha, and sigma. And it reports things like the mean and the standard deviation and so on. Let's just do that again, but to the print argument, we're going to pass a vector of names of the parameters we want to print so we don't see all of our generated quantities at the same time. So now we get something simpler like this. I'm just going to try and rearrange my window, get it all in the same line for you. So it tells us we ran 4 chains, each with 2,000 iterations. The first 1,000 by default were thrown out as warm-up. That's when the MCMC algorithm was being adapted. So we can't actually look at those for inference. Thinning is 1. In other words, there's no thinning. So there's no throwing out of some of the chain values. So it tells us that after warm-up across all chains, we have 4,000 samples. And then we get this information here. We've got the mean. So that's the mean of the posterior. We'll come back to this in a sec. Standard deviation. So that's the spread of the distribution of the posterior. Standard deviation of each one. And then we've got our 2.5%, 25%, 50%, 75%, 97.5% quantiles. So this is the upper and lower 95% credible interval and the upper and lower 50% credible interval, and this is the median. We have our effective sample size, which here is not that far off our total number of samples because we have very little autocorrelation in our chains because it's a very simple model, easy to sample from. And we have our hats, which round down to 1. Fantastic. That's what we want. And there's no warning here. Importantly, you will get warnings. We're going to talk about the important warnings later, but there's no warnings. That's great. So the one thing that's probably new here is this SE underscore mean. So this is the standard error on the mean due to MCMC sampling. So this standard deviation, which reflects the sort of the width of the posterior, is what you would normally be thinking about as the standard error on a parameter if you fit this with like the JLM function in R or the linear model LM function. This is error due to the MCMC sampling. So if we had very small effective sample sizes or we had not run many iterations, if there's a lot of error in our MCMC chains, then you start to get, this will start to creep up. Right now it's rounding to 0. So that means that if I had just run this multiple times with different seeds, I would expect to see a range of means here corresponding to the standard error on my from my MCMC chains. So this is the sampling error mean from the MCMC chains. You want this to be as small as possible. And this sort of tells you how much precision you have in your mean. Whereas this is the uncertainty on the posterior itself. So usually this should be close to 0. If it's not close to 0, you're probably going to see that in your effective sample size being small or your R hat being big. But that's what that is. Any questions about what we're seeing here or about that standard error on the mean versus standard deviation? Okay. So we talked about shiny stand. Shiny stand works on any stand model. So we can call that, and we would get this thing that we can then dive through interactively to look at our distribution. So this is the posterior on our intercept, and the standard deviation reflects sort of the spread of that posterior. Okay, I close that to come back. So there is a built-in plot function in RStan. Here I'm telling it I just want to worry about those 3 parameters, or this plot would be very, very tall. And by default, it makes one of these dot and line plots with, I think, the mean and the 50 and 95% credible intervals. But there are generally other options for plotting that we will look at, similar to what you've been using before with BRMS that we've talked about, that are more customizable, and there's more options. But there is that default built-in function, and here I've pointed you to the help for some of the built-in plotting functions within RStan. generally I'd suggest you use the Bayes plot package for plotting, which is maintained by the same people and sort of is a subsequent iteration of plotting Bayesian models. But as an example, if we were to call this stand dense function, we get these posterior density functions for our 3 parameters. So let's use the Bayes plot package, as I said, and to do that, we just need an input of an array, because the Bayes plot package works with any array. It doesn't matter what package you've used to fit your model. So we can extract an array of our posteriors with the method as.array, and that's because, so if we look at the class fit, it is of class standFit. So what we are calling there is as.array.standFit, because the S3 model class, and R means that the as.array then looks for as.array.standFit because the class is standFit. So that's what I would need to know in order to find the help for this. And as you'll see here, there's several methods: as.array, as.matrix, as.dataframe, or do as you would expect. They extract arrays, matrices, and data frames. So here we need an array for Bayes plot. So I've extracted it as an array, and if we look at fit array, so it's a 3-dimensional array, and the dimensions are the number of post-warm-up samples per chain, by the number of chains, by the number of things that we have recorded. So we've got 3 parameters, and then we've got a whole bunch of generated quantities here. So if I were to look at fit array, so this is the first sample from the first chain across all the things that I am recording, we get this vector out of it, which is all the things that are recorded. And the ones that we probably care most about right now are our 3 parameters that come first. So once we've extracted that, we can pass it to our Bayes plot function. Here I'm using MCMC trace to look at trace plots. This looks pretty good to me. This looks about as good as it's going to get. We got our nice fuzzy caterpillars. They're all over top of each other. They're not wandering away. There's not massive autocorrelation. They're not separated. And that's as you'd expect, because our hats and our effective sample sizes also looked quite good. But it's always good to visually inspect our chains. So one common way that you might work with the output would be in a list format, which is often easier to work with than an array. And a common way to get there is with the extract function. I guess there isn't a as.list function. The as.list function is the rstand extract function. So if I run that and I look at the names of post, now we have a named list, and each element is a parameter or a thing that I had in my transform parameters or in my generated quantities. And I have an element for the log posterior density, which is this LP __ thing. So if I were to look at post beta, I now have a vector. I could pass that to a histogram. So if I do post beta, this is my posterior distribution in the form of a histogram for my slope parameter beta. So that list is quite helpful for working with. For example, I could use that. Here I'm going to plot a bunch of draws from my posterior of the linear regression that I fit over top of my observations. So I'm going to take 200 draws, because I'm just going to take the first 200 in this case of my intercept and my slopes. I'm going to give the geome AB line some transparency, so this is only 0.1 opacity. And then we get this. So this is our data in dots, and then each one of these lines is a draw from our posterior. We've taken a draw from the intercept, a draw from the slope, and importantly, they're matched up. So any correlation between these 2 parameters is embedded in our visualization of the posterior fit. And so if you did this a whole bunch of times, you're sort of getting a continuous version of a confidence interval, or in this case, what we call a credible interval. If we did this a whole bunch of times and we took the quantiles, we would get our credible intervals. But visualizing Bayesian models like this is often a helpful way to visualize uncertainty. Okay, so we've already extracted it. I've just written this here again so it's explicit. So we have our named list post. And if you remember, at the end of our file, we had our generated quantities. And one of the things that we generated was something that we called posterior predictions. So I'm going to save those into a PEP for posterior predictions. And what we have here, if we look at the dim of PEP, we've got 30 by 4,000, and that's because we've got 4,000 samples across, remember our data was of length 30, and we've created a posterior prediction for each of our observations. So there's 30 of them, 4,000 samples. So we end up with a matrix that's 4,000 by 30. And we can make our own posterior predictive plots like we have before, or we could use something in the Bayes plot package. So let's use the common one we've used before, which is a very common default, which is the posterior predictive check with a density overlay telling it that I want my observations to be my y in my data frame, which is the thing that I modeled, and that I want to take the first 25 of my posterior predictive simulations. So I'm just taking the first 25 of my 4,000, just to have something manageable to look at. In a perfect world, if I had a lot of autocorrelation in my chains, I probably wouldn't have wanted to take the first 25. I would have wanted to take a random sample of 25 because the 25 might be more related to each other than a random sample of 25. But I know that I have very little autocorrelation here. So for simplicity, I'm just taking the first 25. And we end up with a plot that we are familiar with from before, and this looks good to me. Our data are kind of right in the middle of our simulated data. Seems to have the same shape. Doesn't represent an outlier. It seems plausible that our data are coming from the same generative process as what our model is creating. So that's great. That's what we want to see. And so that is how we can do a posterior predictive check using that generated quantities section. And we can see how it was convenient there because we could use all the data that was already set up and do it within Stan. But there's no reason we have to do it within Stan. We can do it within R. In fact, I believe BRMS does the posterior predictive checking in R itself after the fact. So I'll just show you an example of how I might do that in R if I wanted to create it myself. There are so many different ways you could do this. This is one way to do it. All you need to do is iterate through your posterior samples of the parameters, generate your prediction, and then sample from a random number generator, in this case R norm, because we have Gaussian or normal observation error, with the appropriate scale of the observation error from your posterior. So I'm setting the seed so that we all have the same thing to look at, so it's reproducible in terms of the random number generator. I am saying that I want to take 8 posterior predictive simulations. The way that I'm going to go about this, and there are many ways, is I'm going to create a list and I'm going to fill in the elements of the list with my different simulations, and then I'm going to bind them into a data frame. This is a nice way to work for several reasons, but one reason in particular is it's very memory efficient. In R, if you build a list, it doesn't actually copy the list every single time you iterate through the loop. If we were doing this in a data frame or a matrix, that's not the case. It would actually be creating a new object with every loop iteration. Doesn't really matter for the simple example, but for anything of realistic complexity, that can be a lot slower and less memory efficient. So a common way I would work would be to create a list. Sequence length is just a fancy and safer way of creating, I need to actually run nsim, of creating a sequence of length and sim. So that's the same as just going 1 to 8. or 1 to n sim. It's safer because if my n sim was 0, I get a loop of 0, whereas 1 to 0 is actually 1 to 0. So it's more, you're protecting yourself or another user in your loop. So I've gone through my loop, and on each one, I'm going to create a data frame or the tidyverse tibble equivalent. I'm going to save something in my I so I know which iteration I'm working with. I'm going to create my y posterior predictive, y underscore pp, I'm calling it, by calling our norm of length of the number of observations we have, mean equal to my creating my mean here, simple linear regression. If this was a GLM or some more complicated model, this would just be have more in it, but it would be the same principle. And then the magnitude of my observation error going to our norm is from my samples from sigma, from my posterior. And that's it. So if I run that, I now have a list that I've called out for output. And each element is a little data frame that has my predictor, it's got my iteration, and it's got my simulated observations. And I should have the length of out should be 8. And then I can bind them together into a data frame. One way to do that is the bind rows function. The other way, you might have seen do call rbind is the base R version, if that's simpler to you. But bind rows takes the list and turns them into a data frame. So now we have a data frame, starts with iteration 1, ends with iteration 8. Now I'm just going to do some more data manipulation so I can actually plot this. I am going to call that a posterior prediction because I'm going to bind on the real data so I can plot the real data with the simulated data. Again, I'm going to use bind rows. I'm going to give it my simulated data and then my observed data, calling that type observed. All of that just to create this data frame that has all my predictor values, the iterations, my real data, I'm calling iteration 9 because I just need to have some value of where I want to put it on the plot. And my type is either observed or posterior predicted. That was so I could pass it to this ggplot function with a facet wrap by iteration to make this plot. So now I've got 8 simulations from my posterior with new observations, colored in blue, and my real data in 9. So a fun exercise is to do this type of thing, but don't actually color which one is observed. Hand it to a colleague. Ask them if they can pick out the real data. If they can pick out the real data, there's something about the properties of your observed data that you have not captured in your model, and you may need to revise your model. Like, what was it about the data that let them pick it out? And that is a key to what features are missing. And if they can't, if multiple colleagues can't figure out which one of the observed data, you've done your job. You're generating data that are consistent with the properties of your observed data. So the point here is just to say there's nothing special happening with the posterior predictive simulations. You can do it in R, you can do it in Stan. The question is whether or not you find it easier to do the data manipulation yourself, or if I go back to lm.stan, control dot, do you find that easier, or do you find this easier, and then you're using all of rstan's machinery in the background to format the data for you so you can work with it. And so when might you prefer one or the other? Well, I think, the obvious thing I've harped on is which do you prefer? That's just a preference thing. There are some cases where it might make sense to do it explicitly in Stan or R. A common reason to do it in Stan would be if you're using some more esoteric math function within Stan, within the model, and you want to be able to use it within the generated quantities rather than try to reproduce it yourself in R. That would be a common reason to do it in Stan. For much more complicated models, it can get much more complicated to do it yourself again in R. You may be more likely to make a mistake if you're doing it yourself in R separately. So then it can be nice to do it in Stan. You have a little more flexibility if you do it in R yourself in terms of what you are simulating, without having to refit your model if you want to create new posterior predictive simulations. So that would be an advantage to doing it in R itself. Okay, so let's move on to a nonlinear model example, something a little more exciting. We're going to look at this growth model. I have opened up the file 09 stan coding growth in the base folder or the exercises folder. I'm going to start by loading rstan. Now I am going to use parallel processing by setting the mc.cores option, telling Stan to not recompile if I haven't changed the model with this rstan option, and load dplyr and ggplot. We are going to work with some Pacific Cod biological samples from the DFO Synoptic Bottom Trawl Survey in Hackett Strait and West Coast Vancouver Island. So I'm going to read in the data. So if we look at our data frame, what we have are lengths, ages, and a survey ID. So we've got those two surveys. This is for a subset of Pacific Cod. Each row is an individual fish that has been sampled. I am going to add just a 1 to the number of data points in my data set, just a column for an identifier. That's going to make it easy for me to join data sets together that you will see later just for visualization purposes. So if we plot out our data, we can see we've got our two surveys, age here, length here, commonly like we see for fish where we have asymptotic growth. Fish are getting longer quite quickly when they are younger, and then at some point it starts to level off. The data, we don't have a lot of data where it levels off, but we can see that it starts to level off. And so we want to fit a growth curve to this. Common growth curve would be the von Bertalanffy growth model, and that's what we're going to be fitting today. And there's a question about whether or not growth differs between these two surveys. And that's something we're going to look at as well in this model. And that's actually a question that has come up frequently at our stock assessment meetings. And one of the ways we've dealt with that is by doing exactly what we do here, which is asking whether or not the posteriors for these two surveys are substantially different from each other. So whether or not there's evidence for different growth in different regions, and therefore whether or not we should be considering multiple stocks or one stock. So if we open up the vbbasic.stan, we can go there in the Files menu in RStudio. I'm going to click Control-VB-Basic to jump there. So here we have something like we saw before. At the top, it doesn't look really all that different. We've got a number of rows of data. We've got our length data. We've got our age data. That's going to come in as a named list. We have our parameters. Things get a little bit fancier here because many of our parameters have a lower bound of 0. So we've got our k, L infinity, and sigma parameters. So the k and L infinity and T0 are part of the von Bertalanffy growth equation. T0, the theoretical length at age 0, can actually go below 0 when we fit the curve. So we're letting that go below 0. We're saying these have to be positive. So L infinity being our expected length at infinite age, basically where it asymptotes out, and k is controlling the curvature of how we get there. So then we place some priors on these parameters, and this is a case where you have to think a little bit more carefully about them. K is going to be relatively small, we know from fitting these models and other fish. L infinity, we need to make sure that it can go up into a range of, roughly 60 to 80, somewhere in here. We probably expect it to be around 75, maybe. So we want to make sure we pick a prior that constrains the sampler from going way too far off from that, but is going to let the posterior get up there without necessarily constraining it. T0 we know should also be small, just from our knowledge of von Bernoulli growth curves. And it's a symmetric prior. These two are half normals because we've set the lower 0 bound on them in the parameter section. And then we've used a half student T on sigma. This could be a normal as well. This just has slightly heavier tails again than the normal because we've given it degrees of freedom of 3. The student T with a very, very big degrees of freedom is the same as a normal. It approaches the normal. Scale of 2, so that's basically equivalent of the standard deviation for the Gaussian distribution. And so the only thing that makes this harder, more challenging, or really different from linear regression is that we have a nonlinear equation, this fancy thing in here, which is generating our expectation. So instead of just intercept plus slope times a predictor, or multiple predictors times multiple slopes, and so on, we've got a nonlinear equation in here, so we call this a nonlinear model. And this is just the equation for the von Bernoulli growth equation, Linf times 1 minus exp negative k times age minus t0. Here we are giving it Gaussian observation error. And think for a second about whether that makes sense or not. Does anyone have any thoughts on what the issue is with that? So this is a simple model. It is frequently used in practice, but it assumes that the errors are symmetric around the expectation for length, which is probably fine for large lengths for older fish. As we get closer to 0 length and 0 age, we would run the risk of this allowing for negative lengths in our posterior, which probably isn't ideal. When you're predicting negative lengths, people get worried. But I've used normal here just to keep this really simple. And it is a common way that it's done. And it's probably fine here because even at age 0, we're still staying away from length 0. We're unlikely to be having a problem with approaching 0 itself. But perhaps a theoretically better data likelihood would be something like the log normal or the gamma, which are distributions that will force a positive distribution and will also can be more skewed upward, which is probably what the data actually look like. But I'm not doing that here just to keep things simple by working with the normal likelihood. So I'm going to go back, hit the back button to where we were. Are there any questions about what's happening there? Okay. So if we go into control period VB norm dot stan, move my head. This is just like what we saw before, but I've added a couple other bells and whistles that are going to make our life easier. So the first thing I've done is instead of hard coding the scale of the priors, I have created a vector of length 4 that's going to hold my desired prior standard deviations. So I've told it it's got to be length 4. I've told it that all of these must be greater than 0. And then I've placed them here in order in my priors. And that just lets me manipulate the scale of the priors in R without having to recompile the model and edit the .stan file every time I want to change them. So that makes it easier to experiment with priors and look at their influence on the model. So that would be a common way of building a model in practice. I've added this thing that we talked about before, which is I am adding a flag that lets me sample from the priors only. So I've added an integer, lower 0, 1, 0, upper of 1. And so By default, I'm going to make that false so that I do sample from my observation likelihood. But if I make that true, then this gets excluded. I'm only sampling from my priors. And then I'm adding on the same generated quantities we had before. So my posterior predictive simulations and my pointwise log likelihoods, which I think we will finally use. And then later we will talk more about what they actually mean. So otherwise, this is the same as before, but it's got some extra bells and whistles. I'm going to click the back button. So in order to fit this, I have to create my named data list to start. So I'm creating dat. The names of dat are the different elements that were in the data section. I am saying prior only is 0, so that's false. These are my prior SDs. I've actually increased the L infinity standard deviation, which makes more sense because if we draw out the D norm, so if I wanted to draw out the D norm, this is a good thing to know how to do. I could do something like, let's see, I want to look from 0 to, let's say 200, length out of 100. So that's just created a vector from 0 to 200 of length 100. And then I just want to plot x, D norm of my x, vector mean of 0, standard deviation of 200, because that's what my prior is. So if I do that, and then I'm just going to say ylim equals 0 to 0.002. And I could get fancy and say type equals L. So there I've just quickly, something I frequently would do when I'm trying to develop priors. This is the shape of the prior that I am putting on that L infinity thing, which is the expected length at maximum possible age, at infinity age. So we know it's got to be somewhere up in here. So we want a prior that is going to penalize as we start to get out to crazy values that we know we're not going to end up with fish that are this large, but that's not really influencing the posterior too much, getting up to where we expect to be. So that's where I've chosen 200. If I had done 100 like I had shown before, obviously I need a higher y-axis. It would look something more like this, and you can see that sort of at 70, it's starting to curve down more. So I've increased the standard deviation to have a little bit, to leave it some more flexibility to estimate where I think that L infinity should be based on my knowledge of Pacific cod. And these other ones are similar to before. My sigma is at 10. That could perhaps be tightened up, but I'm going to leave it there for now. So we have our named data list, and then we can sample from a model just like before. So we give it the location of our model. Here I'm using here because I'm in an RMD file. I want to make sure it works on everybody's computer. But we could have just set the working directory. You'll see here that at the beginning there was a pause, and that's because I set it up with parallel processing and the options at the top. And so at the beginning it sort of was initializing those various chains. And then if you look at the output, you'll see here that the chain 1, chain 4, chain 2, chain 3, we're seeing the output come back from the various chains at the same time because they're sampling in parallel. That's how we can make sure that it is actually doing what we want it to do and sampling in parallel. And you can see they all finish at roughly the same time in 1.5 seconds on my computer. When you fit this the first time, you're going to have to wait for this to compile. And I set the seed just so it's reproducible. So we should be running the same MCMC stochastic chains. So similarly to before, I can print, and here I'm just going to print those 4 parameters that I care about, not all my generated quantities, to keep this simple. So we have the same output as before. You can see that there is a little bit of standard error on the mean of L infinity, and where our effective sample sizes are far smaller than before. This is a harder model to sample from, and nonlinear models often are harder to sample from. Our R-hats are 1.01. Our effective sample sizes are considerably lower than the total number of samples. They're still probably reasonable here. We're looking for over 400 is sort of a rule of thumb that goes around. But as this gets smaller, we do end up with more standard error on the mean. So this is a larger parameter value than the others. And so on the scale of that mean, there is a little bit of a standard error from the MCMC samples themselves. So that's saying that if we did this over and over and over, changing the seed or letting it pick a random seed each time, the distribution of the means that we get in our output here would follow a normal distribution with a standard deviation of 0.06. So you'd have a little bit of variation in the mean. So that tells us that it would be, be silly to report this to 2 decimal places, for example, because it's going to change each time we sample. If we really wanted to report the mean to 2 decimal places, we would want to have more samples so that our standard error on the mean gets smaller and there's actually some stability in the mean that we're getting out of our stochastic MCMC algorithm. Whereas this one is about the spread of the posterior that we will look at. So as we said before, we can extract the posterior in various formats. So extract, like we used in the last linear regression example, will create a named list. As.matrix creates a matrix, and what it does is it concatenates all of the samples for each of the chains after warm-up, row after row after row. So now we've got 4 times, what have I sampled? I did 1,000 iterations, so the first 500 were being thrown out. So 500 times 4 is 2,000. So we have 2,000 rows. Those are MCMC samples. And these are all the things I'm recording. There's a ton of them because I did the posterior predictive simulations and the pointwise log likelihoods as well, which is probably slowing things down a bit because it's got to monitor all those things when it brings them back together at the end in the object. So it makes a bigger output object. The as.array is very similar to as.matrix, but it doesn't collapse across chains. So instead of having 2,000 all together, it's got 500 by 4. So those are the 4 chains are still separate. As.array is what we would want for Bayes plot that we've looked at. And as an example, we could look at here the first 4 elements here. So those are our parameters that we have sampled. As.dataframe creates a data frame. If we look at the dimensions of that, sims.df, it's similar to the matrix, but it's in the data frame format, so we've got columns that we can reference. And you could use things like the reshape package or the tidyr package to manipulate these into, say, a long format data frame for plotting, which I think we will do later. So if we work with that array, we can look at the MCMC trace. I just need to make my window larger here. Actually, I may need to dev.off. Try that again. I'm telling it I just want the first 4, otherwise I'm going to get thousands of panels and this will take forever to build. I think actually it'll just do some of them, but it'll be too large to look at and it'll take a long time to build. So these are our parameters. So our K parameter, length, sigma, and T0. These look pretty good to me. They're all overlapped. They're not drifting. There's not massive autocorrelation, and there's not outliers that are wandering off for some of the chains. So we can do lots with the output ourselves. We can take those data frames, those arrays, those matrices, do whatever we want with them. But there are some really nice utilities within the R package tidyBayes. And this has a really compact syntax for taking a STAN or a BRMS model, grabbing elements from the posterior and turning them into long or wide format data frames that are easy to work with dplyr or ggplot. So a common one that you might use would be something called gather draws. To that, I'm going to feed it my STAN fit. And I'm going to say I want 20 draws I'm setting the seed so that I get the same 20 random draws each time I run this, just for reproducibility of my script. And then the thing that I want to grab is my generated quantities of my length sim, because I'm going to do a posterior predictive check here. I generated something called length sim. And then I'm telling it that that is a vector, so it needs to be indexed by something, and I'm going to call that index I in my output. So once I've done that, if we look at what we get a tibble or data frame in the tidyverse, where that I, that's what I told it to call my index of the vector of the observations. So I've got my I column, I've got my chain, my dot chain, so these are 1, 2, 3, 4. I've got the iteration, which I think is unique for each chain, and then I've got the draw, which I believe would be unique across all chains together. So they're just different indexes on my MCMC iterations. So this should go from 1 to 500, and this should go from 1 to 2000. I've got the variable that I extracted, length sim. So I think you could have a unquoted vector of things you want to extract here. You can experiment with that. So variable, the name of the thing, and then the value of the thing. So this is the value of the length sim. So we did that. The nice thing about this is you can imagine you can pipe this now right into a ggplot and make a visualization. So I mentioned at the beginning that I saved a column I into my data, and that was so here I can join it on and it will match the I here. So I'm going to join here, and it says it's joining by the data iteration. So I did a left join there. So what I've done is I have added now onto my data frame, it's joined based on I, and now I've got my length and age from my data, repeated each time for each of my 20 simulation draws. So here I'm plotting age and the samples, so the dot value. So these are the simulated observations of my length. 20 of them overlapped with a 20% opacity. So if we go back to our model, which was control dot VB norm, one thing which I'm realizing now I glossed over before was that unlike the first model, we have used the transform parameters section. And so in that transform parameter section, I created something that I said is going to be called predicted length. It's going to house my predicted lengths. It's going to have the same length as the number of predictors in this case. I then iterate over it. Because there's no data likelihood in here, it doesn't matter if I'm doing a loop here in terms of speed. And then I'm going to record the expected length for each age in the data. So this is creating the expected value. This is the mean, the expected mean. And this is just that nonlinear von Bertalanffy growth equation. And because I've done that calculation here, one, I've saved it, and we're going to plot it now. And two, I get to reuse it. So instead of having to type that out over and over, make my code harder to read, possibly make a typo, I do it once. Now I can use it below in my data likelihood, and I can use it here for my posterior predictive simulations, and here for my pointwise log likelihoods that I'm keeping track of. So because it's in transform parameters, it gets monitored and saved, and I can reuse it below. If I had it in the model section, the computations get done and then it gets thrown out. So it's not recorded in the MCMC sampler, and I couldn't use it below at the end in the generated quantities. So because I have recorded that in the transform parameter section, it's available to me, and I can, again, use gather draws to create a long format data frame that takes 20 samples from the posterior of my predicted lengths. So I'm going to run that code. So it looks similar to before, but now we have predicted lengths instead of simulated observations. Again, I'm going to join on my data. I join on my data here, I actually use it, and that is to plot a combination of the data, which is what we see here in the dots. And it's actually overplotted on top of itself over and over because I left joined it on here, but it doesn't really matter for our purposes. But I've got my points, and then these are 20 lines that are drawn through the data based on the predicted lengths in my model. So the previous one, if we look back at this is the spread of new simulated values from our model, which is what Bayesians often are concentrated on. And then this is the spread of the expectation, which is what you're probably familiar with looking at in terms of predictions from linear regressions or GLMs and R or other maximum likelihood models. This is uncertainty on the prediction or the expectation. So what are we looking at? We just talked about that. The other thing we can use gather draws for is to grab parameters themselves. So before we were gathering generated quantities or transformed parameters, but we can also just grab parameters in a long format data frame. You'll notice that these are unquoted, as they're often called, names of the parameters that we want to grab, and that's because it's using internally something called non-standard evaluation, or technically tidy evaluation, which is a version of non-standard evaluation. That just means that internally R is going to guess that these are referring to things that are called that as opposed to the objects K, LM, T0, and sigma. It just saves, that format saves the user having to, put quotes on everything. So it's a little cleaner. That's the way it's written. So you give it an unquoted vector. In the second argument, we looked at the help for gather draws. You'd see that the second argument is ... and the ... takes expressions that represent the variables. There is extensive writing within the details about how that can be indexed. So here I'm grabbing those 4 parameters in the ... of my function. I haven't set the seed, so it's going to look... Actually, we don't need to set the seed because we've taken all of the draws here. I'm not just taking 20, I'm taking everything. So now we have the similar long format data frame, but our variable column, if we look at table.variable, we've now got 2,000 of each of the variables, our parameters, and they are one after the other in a long format data frame. And that is convenient because we can then pass them on to ggplot. I'm going to make a histogram. I'm going to use facet wrap by that variable, free x scale so that they have their own x scales, x limits, because they're on quite different scales from each other. And we get that. So now we've quickly made a posterior density histogram plot of our 4 main parameters. And we could summarize that however we wanted in terms of quantiles or so on. Okay. So this isn't going to seem all that useful yet, and I promise it will be more useful when we talk more about this, but we calculated those log likelihood point-wise values, so for every data point. And that is so that we can use the LU function from the LU package, also written by the Stan folks, to calculate these information criteria. We're going to talk more about these. This is just as useful as looking at a single AIC value, as in not useful at all yet. But because we have those log underscore likes in our generated quantities, the point is we can pass it to the LU function that we are going to use for model comparison eventually. Are there any questions on that version where we just fit a simple single growth curve to all the survey data? Okay. I'm going to go, this time I'll show doing it from the File Explorer. I'm going to go to the VB folder, VB norm regions. So here I have extended my model slightly. And what I have done is set it up so that each of my parameters in the growth equation are indexed by survey ID. So I want to allow for different growth in the two surveys, but they're going to share one magnitude of observation error, sigma. So all I have to do that is to add a survey ID. So I'm going to create this in R, and it's going to be an index of 1 and 2 for my two surveys in this case. And here I'm saying that's lower of 1 because I want to help myself out, but I'm not specifying an upper so that I could fit this to different numbers of surveys. We could drop that, but then I could do something dumb and my model would fall apart. So I'm just protecting myself for other users. And then I need something which is the number of surveys, and that is needed to dimension my parameters. So now, instead of it just being real lower equals 0 k, it's real lower equals 0 k with length of n surveys, is what the square brackets are saying. So now we're going to have, assuming n surveys is 2, which it is going to be in this example, we're going to have 2 k's, 2 LMs, 2 T0s, but 1 sigma. Then we're going to loop over our observations and create our expected length using our von Bertalanffy nonlinear growth equation again. And we just need to make sure that we index each one by survey ID, which itself is indexed by I. So survey ID is going to be a whole bunch of 1s and 2s, and we're just going to pick out, is it LMF1 or LMF2? K1 or K2, T0, first one or second one, indexing our age, which is our predictor here, by I as well. And that creates our predicted length for each observed age. Again, the priors are the same as before. We're allowing them to come in as named data list vectors of length 4. I've allowed the ability to do prior predictive checks, which we haven't actually done yet, but that's what that allows. And then everything here is the same. We don't need to worry at all about having the multiple surveys down here because we can reuse our predicted lengths that we generated up here. So this code is exactly the same. This code is exactly the same. All we had to do was worry about expanding our parameters from singular values to vectors, or in this case, I think they'd be called arrays. A real of length 2, length 2, length 2, length 1, and then expanding our growth equation here. And then supplying these two extra data elements. So that's what we need to do to expand it. I'm going to close this and go back. I am going to save my data to a new data frame .2 so I don't lose my original one. So if we look at our data, so we've got 2 surveys here, and we need to create 1s and 2s to represent our different surveys. You could do this lots of different ways, like with an if else statement if you wanted. One quick way is to use a factor, which turns it into a character value that's got an associated numeric order. If we take the integer of the factor, you get the factor levels as integers. So if I look at that, I get a whole bunch of 1s and 2s. So all I have to do is wrap my survey in as.integer factor. And the point is just to create this vector of survey IDs. And so it starts off with a bunch of 1s, and then it finishes with a bunch of 2s, because I'm going through survey 1, survey 2. Number of surveys is 2 in this case. And then I'm going to sample from my model. It spins up the 4 chains on separate cores, samples from them, gathers everything back together. A little slow here because there's lots of generated quantities and transform parameters that I'm saving. And then I'll print them out. I'm going to make my screen a little wider like that. Oh, almost on one line. There we go. So this should look the same as before, except that now you'll see that my Ks are indexed by 1 and 2, my LMs are indexed by 1 and 2, my T0s are indexed by 1 and 2, and I have 1 sigma. I have, some standard error on the mean from the MCMC algorithm itself on my LMF as before, slightly more than before, probably partly because you've got half the data now for each LMF. But everything else generally looks okay. My effective sample sizes are above 400. My R hats are rounding down to 1. That's great. I'm going to drag this back over. Try to find my way back over here. Okay, so I'm going to take my MCMC samples, my posteriors, as a named list. There's an S in there. So those are the named list elements that I have recorded. Now I'm going to show you some various ways that I might visualize these posteriors. So if we wanted to visualize the distribution of the simulated observations, so the predicted new observations, that's our thing we call length sim in the generated quantities. I can summarize those with a quantile. Say I want to plot a ribbon or a dot and a line. So I can use the quantile function, and because I now have 2,000 as the number of samples and 1,000 as the number of simulated lengths that I have, one for each data point. So I want to go through each one of those observations and summarize those 2,000 MCMC samples. So I basically want to apply the quantile function to each column of my matrix. And if you're familiar with the apply function in R, that's exactly what we want to use. If we look at apply takes an array or a matrix. Here we're giving it a matrix. Margin is the second thing, and that is, in this case, 1 for rows, 2 for columns. So I want to summarize over columns. So I'm going to say 2 is the second argument. The function I want to apply, which is quantile, and then the fourth argument is ... And if I read about ... it passes arguments to the function. So in this case, I want to pass the probs argument, because if I look at quantile, we know that there's a probs argument, which is the probability threshold in the quantile. So I want to pass over probs equals 0.9, probs equals 0.5, and probs equals 1. So this is the upper and lower 80% credible interval, because 0.9 minus 0.1 is 0.8. And this is the median. I could have just passed median here. Same thing. Okay, and then the other thing that I want to visualize to try and hit this home is the quantiles on the credible intervals on the expectation. So that's the thing that we call predicted length in our transformed parameters. So I'm going to do the same thing. I'm just going to add an E underscore for expected. So I've got my upper, mid, and lower. And then I'm just going to plot what I have created. So I'm plotting my data. So my data is D, age. The thing that I've extracted here is D. Age is the observed age. MED for like medium or middle. Median value. So this is our median value coming out of our simulated lengths. And then I'm going to do the same thing for my expected values. I'm going to do a ribbon. So if this is going to create a confidence interval, a credible interval for my expected and my observations. And then I'm going to plot the actual data here. So let's plot that. And I guess importantly, we also colored and filled the color by survey ID. So we've got our observations here as dots. We've got two sets of ribbons. We've got the inner ribbon is the credible interval on our expected length. And then the outer ribbon is our credible interval on new observations of lengths of fish. So if this fits the data well, we would expect that 80% of the dots for a given survey should be within this wider ribbon. And that is not the case for the expected one, the expected value, credible interval, of course. So we could check that if we wanted to make sure that we had approximately the right coverage. So that's great. We've visualized our model. We can start to see here, there's a little bit of a difference. ELINF is probably a little bit higher for West Coast Vancouver Island compared to Hackett Strait because it's starting to, it curves up a little bit higher here. But in general, they look pretty similar. We're going to test that statistically in a second. First, I just want to make some posterior predictive simulations to make sure that my model is recreating is a generative model of my system. So I'm going to extract models from my first fit and my second fit. So the first fit was shared across the surveys. The second fit, I have two independent curves for the different surveys. I am going to just create I here is just going to be 20 random MCMC samples that I'm going to draw. Now I'm actually bothering to pick 20 random ones because there's probably a little bit more autocorrelation in my chains. I want to make sure I get 20 independent samples. They're not one after the other. I'm then going to extract those 20 samples from my first model and my second model, and then we can plot them using Bayes plot. So there's my first model. Looks pretty good to me. There might be something funny going on here, but it's not too bad. If I look at my second one, it's similar, maybe a little bit better. Maybe it has dealt a little bit with this sort of bump in the observed data. It's a little more within the data that we simulate, but not really a huge difference. Here I'm going to group it by survey. So this would be an important visualization to look at in this case because I have ignored survey in my first model. So I want to know, is there structure that we're seeing in the simulated values that we're not grabbing in our model? So that's the first model. That's the second model. We'll go back and forth between them. So maybe slightly better in the second one. Not a huge difference here. There may be other stuff going on that's causing this mismatch here. A prime one I might think about would be potentially year or space. Could be spatial clumping or possibly changing through time. Okay, so I'll now look at some trace plots. I am going to use a regular expression here just to grab only the K, ELINF, T0, and sigma. And the important thing is the caret symbol here. So in regular expression, the caret means starts with. So I want to grab all the parameters that start with K, start with ELINF, start with T0, start with sigma. That's important because in my second model, there's K1 and K2. So instead of writing out K square bracket 1, K square bracket 2, I can use this as a shortcut. And I just grabbed the first 10 here. No, you don't actually have to do that here, but that's just making this array not have all the other stuff in it that I'm not going to use anyways. All the generated quantities and so on. So there we've got our trace plots, looking pretty good to me. So for model comparison, we're going to talk about this next. But for now, we'll know that we can do model comparison with something that's basically analogous to AIC by calculating the leave one out information criteria and then making a comparison here. They are relatively close to each other with relatively large standard errors. There is not a very big difference here. Model 2 is a little bit better, but we also have considerably more parameters. We'll talk more about that in a sec when we talk more about expected log predictive density. But that doesn't really show us much evidence that we are better off with a more complex model. So one of the nice things we can do with this is we now have posteriors for both the surveys, and so we can ask, are the growth parameters from these two different regions, how different are they? And so we can do that. We're going to grab our posterior distributions, again, as a named list from fit2. And as a reminder, if we look at any one of these parameters, like sims k, we have two columns. Let's look at this array. I guess it is you can consider it a matrix here, basically, but it's got two columns. And those are for the first region and the second region, first survey, second survey. So if we wanted to ask, for example, is the difference between these two regions, what is the difference between these two regions probabilistically? So we can do that. All we have to do is subtract these MCMC samples from these MCMC samples because they're already all lined up as we moved through the joint parameter space. So k with the second column minus k from the first column, same for LM, same for T0. And that gives us the posterior distribution on the difference. And then we can plot that or characterize that quantitatively however we want. So, the density is a bit off zero, but there's plenty of posterior density both above and below zero for a k parameter. LMF is a little bit higher for the second region than the first region, but there's plenty that's below zero as well. And similar story for T0. So if we wanted to calculate something that we want to report, rather than just looking at a histogram, we could use the trick we were using before, turning that into a bunch of trues and falses, which gets turned into zeros and ones. This gives us the proportion of differences that are greater than zero. So if we go back to our LMF histogram, this is just counting up how many of the samples that made up the histogram here are above zero, and the answer is 0.78. So there's a 0.78 probability that LMF is greater in West Coast Vancouver Island than Hecate Strait, but keep in mind that a 50% probability would just be completely random and no difference. We could ask something more specific, like what's the probability that LMF is at least 5 centimeters greater in West Coast Vancouver Island than Hecate Strait? The answer is, well, there's only a 0.3 probability, a 1 in 3 chance, basically, that the difference is at least 5 centimeters. So you can sort of come up with numbers that are on a scale, like, do these matter to me? And ask what the probability is for a meaningful difference. Or we could say, what's the probability that LMF in West Coast Vancouver Island is different from LMF in Hecate Strait by more than 4 centimeters? So this is kind of a two-sided thing. Is it more than 4 centimeters one way and more than 4 centimeters the other way? So that's just calculating how many samples are basically to the left of here or to the right of here. And the answer is only about a 0.4 probability that the difference is greater than 4 centimeters between those two regions. So I think I'd conclude that there's probably not strong evidence of different growth characteristics between those two regions in this case. So I think this is an example of moderate complexity, and it's quite realistic, and it's something we actually have used in stock assessment processes. And it's something you can code up quite simply in Stan. Nobody starts from a blank model. If I were going to fit a von Bernoulli model, I would go find a Stan file. I would start with it, and then I would edit it. You start from some existing model and edit from there. One thing I didn't show was the manuals. So the manuals for Stan are quite extensive. So if you just Google Stan manual or Stan documentation, you'll get this site. And that takes you here. And they've actually currently split up the documentation into 3 rather large manuals that are available as HTML and PDF. You've got one that's on models and programming techniques, one on the language itself, and then one on the built-in sort of functions, mostly the math functions. So they're all they're quite extensive. They're available here as HTML. And if you Google anything with Stan, you're probably going to end up with a link that takes you somewhere into one of these reference manuals. So now I want to take an aside to talk about cross-validation, model comparison, and expected log predictive density. We have alluded to this throughout several of the examples with those log likelihood point-wise calculations. So now let's dive into sort of what's going on here, why this is important, and what's happening. So why do we need cross-validation in the first place? So we often want models that make good predictions on new data, but measures of predictive performance on fitted data will, I think virtually always, maybe always, get better with more complex models. But at some point we are overfit to the data and would make poor predictions on new data, and we aren't probably focusing on the important model elements. So here's a visualization of this. So the dots are lines in a linear regression, and we have the black line is fit to the full data set, and then the dashed line is fit leaving out the individual data point that is circled there in gray. And so when we include that data point, which is the sort of the furthest away from the line in this case, it pulls the expectation towards that data point. And every data point that goes into the model, the expectation does get pulled towards that data point. That's the nature of the model fitting. And so if we were to calculate residuals doing that, the black ones here are the residuals from fitting the model to all the data. And then the open circles are the residuals if we did this same procedure for every single data point, if we left out the data point and then calculated the difference between the expectation and the left out data point. That's what we see here in the open circles. And so the point here is that the open circle left out data point residuals are always further away from the expectation than the full data set fit residuals. So what we want is some way to quantify the goodness of fit using these left out data points to know how good would our model be at predicting left out data, but we also want to do it in some way that is computationally feasible. So there's several common types of cross-validation. One that's often called k-fold, which means that you split the data k times, fit to each data set, that where you've left out chunk k, and then you test the goodness of fit on chunk k. There's leave one out, which is the limit of k-fold, where k is the number of data points. You leave out each data point one at a time. That's what I was showing in the visualization there of the left out residuals. And then just some terms that I'm probably going to end up using that are frequently used in this field. Sometimes we talk about in-sample versus out-of-sample data. So above in this k-fold example there, the in-sample data are the data that you fit to, and the out-of-sample data are the data that you test on, you've left out of your model. Sometimes that's called in-bag versus out-of-bag data. That's, I think, more common in the machine learning literature, cross-validation. So there's trade-offs involved in your choice of how you do your cross-validation. For a low k-fold, so a few number of splits, you've got some bias in the performance assessment because you're fitting your model to substantially less and less data compared to the full data set. So your model is going to look worse because you're fitting it to not the full data set. And leave one out is sort of minimizes that bias in performance assessment, but it's computationally hard because you've got to fit your model the most number of possible times to do your cross-validation. So once you've done your splitting and your fitting and your testing, the question is, what do you test? And the answer is really whatever you care about. So often in applied context, there might be something that you actually care about. So classification rates, or sometimes people care about root mean squared error. That's all great. Without a specific measurement of interest, the expected log point-wise predictive density, ELPD, that we're going to be talking about is a nice quantity to work with for several reasons. And the reasons are that it's as you'll see, it's a measure of goodness of fit that is consistent with the likelihood assumed when fitting the model, and it fully encompasses the uncertainty in the posterior distribution as well. So what I'm going to try to do here is illustrate stepping through what's going on when we calculate the expected log predictive density and why it makes sense. So if we start off here, so we've got our data with the dots here, open circles, y and x, a linear regression. And let's imagine that we have fit with MCMC sampling a model to our data. So what I'm showing you here is one MCMC sample. So I've taken the intercept and slope from one MCMC sample and I've drawn my line on the data. That's what we show with a straight line here. And then what we're interested in is looking at how well is that solid point, where there's the red line coming off of it, how well is that predicted by our model, including our estimated observation error, which defines the possible spread of observations around that expectation. And so what I've drawn there is basically the density coming out of our observation error based on that mean. And the distance of that red line is a measure of how likely that data point was according to that MCMC sample from the model. So if you recall, each MCMC sample can be visualized as a fit through the data. So this is 20 or 50 something lines, each one being an MCMC sample. And so we can do the same thing over and over and over for each MCMC sample. We can calculate the height of, in this case, the Gaussian error distribution, so the d-norm function. And the length, we're going to record the length of those red lines. So now we're looking at how likely is each data point. Here we're just looking at one data point, but ultimately we're going to do it for all data points. And then we're going to get a distribution of how good it is across our MCMC samples. And so if we did that, and we plot out the distribution of the length of those red lines, now I'm showing that distribution for 6 data points, we get these histograms. So here we've got the likelihood on the x-axis. Those are the lengths of those red lines from the previous slides. And then we've got the distribution here. And then we want to characterize these distributions in some way. And what we're going to do is we're going to take the mean of these distributions for each data point. So the red line, the red vertical lines here, are the means of these distributions of these point-wise log likelihoods. And if we take the sum of these point-wise, i.e. for each data point, average or expected likelihood, we have the log score. If we do this with left-out data, we call it the expected log predictive density, the ELPD, sometimes called expected log predictive, or ELPD-LOO, for clarity that we mean on left-out data. And it's a measure of how likely the observations are. So with ELPD, higher values are better. It incorporates the full posterior uncertainty in the calculation. The value reflects the likelihood assumed in the model. The values are dependent on the observed data, so we can't compare the values across data sets, just like how we can't compare AIC across different sets of observations. They're scaled by the data we observe. They're useful for model comparison. And one major caveat, which is that the ELPD, leave one out, assumes independence in the data points. So that is broken if you have, say, spatial correlation, temporal correlation. Sometimes people do it anyways, but it is breaking an assumption there that the data points are independent. There are other forms where instead of having each data point left out, you can do things like LFO, leave future out, expected log predictive density, where you basically are chunking the data into future sections and you're trying to predict a step ahead, see how well it predicts those data points, and so on. And as you can imagine, you can do the same thing with spatial data. It's all the same. It just depends how you chunk up your data and whether or not you're doing every single data point or whether you're chunking it up by time or by space. So we're usually looking at relative changes in expected log predictive density between models that are fit to the same data on their own. It's not a meaningful number at all, really. And this is a key thing to know here, is that each pure noise predictor is expected to add 0.5 to the fitted ELPD. So if we fit to all the data, calculate our log score, as it's more technically called, we would expect to add 0.5 to that log score. But if we did it with leave one out data, we would expect adding a noisy predictor that has no relation to the response to subtract 0.5. So that sort of lets us scale our expectations. We'll see an example in the code how this works out almost exactly. It's quite amazing. So we've talked about ELPD. There's also something called LUIC for leave one out expected log predictive density information criteria. This is simply defined as -2 times the ELPD, which in other words puts it on what's called the deviant scale. It puts it on the same scale as like AIC where you're used to, where negative values are better, or smaller values are better, sorry. But that's just sort of for, because a lot of statistics works on the deviant scale, on this -2 times scale, and we're used to thinking about it with AIC. There's no reason you can't just use ELPD and never even touch LUIC. So everything we've talked about so far is sort of theoretically consistent. Everything's great, obvious, but the problem is it would be really slow to do what I just showed you in reality for models with moderate amounts of data and reasonable model complexity. Because you have to fit your model to leaving out each data point independently and then calculate what I just showed you and then sum it up. It would take a long time. We'll show that in code on a simple example. Even there, it takes a little while. So these leave one out calculations are computationally hard, but the solution to that is we can approximate it through manipulating the posterior distribution that we already have. That's what the LUR package does. I've also worked it out for you in pure R code in a file that we'll take a look at. And the solution is that the log posterior without a data point is equivalent to subtracting the log posterior of that data point. And we can use importance sampling to transform the sampled posterior without refitting. I have an example of that we will look at. But we're just going to basically call the sample function with weights that are equal to 1 over the density of each data point. And then we have a problem that sometimes we have very unlikely data points or very small weights. And so the LU package does something else fancy to deal with that. It fits a Pareto distribution, which is a heavy tail distribution, to try to smooth those really small weights before it fits them. So you don't actually really need to know this, but that's what's happening in the background. The LUR package has this trick so that we can get at the ELPD and LUIC without actually having to refit our model over and over. And we're going to look at an example now. Are there any questions on those slides while I get the RMD file? I think this file in particular is probably really above and beyond what you need to know just to use it, but hopefully it'll help solidify in your head. And I found it really interesting myself to work through it in R to understand what's going on. So I've opened up 10-loo.rmd from the Bayes folder in Bayes course. I'm going to be using the rstan arm package. We've been using BRMS. rstan arm is similar to BRMS. The difference with it is that it doesn't have to compile the model each time it's fit because it's using a pre-compiled model. It doesn't have as much flexibility as BRMS, but for the models we're using here, it can absolutely fit the same model. So we're going to use that just so this code runs a little bit faster. That's not really the important part of this code. So we're going to simulate linear regression. This is the same linear regression I was just showing in the slides. The slides came from the output of this code. So we've got 1 to 20 are predictors. We're keeping track of how long x is. intercept, a slope, a standard deviation of the observation error, setting my random seed so it's repeatable, and then I'm going to create a data frame called fake, which is not very exciting, but it is X and Y columns. So we can fit a linear model, and here is where I'm using rstan-arm, just so this runs blazingly quickly, but you could do the same thing with BRMS. So I fit my model there. So let's also fit our linear regression, leaving out the 18th data point. Then I'm going to extract the posterior draws, and it's got similar methods. So this is turning it into a matrix. So this is my posterior from the full fit, and then my posterior after dropping data point 18. Then I'm going to do a little bit of trickery here. I'm going to try to draw that normal density function here on my plot by passing the values, a sequence of values to denorm based on my estimated parameters of the intercept and slope and standard deviation. This time 60 plus 18 is just to move my little curve to the right place on the plot, as you will see. And then I'm going to do the same thing for the left out data point. And then I'm going to plot it, and this is going to create the plot that you saw in the slides. I'm just going to run this again because I wonder if I've got the seed right. It looks different than I was expecting. There we go. I had obviously run code multiple times and my seed wasn't set correctly. So now we see the same version that we had in the slides. So I'm just showing you how I created that with our code. So this is the left out data point, and if we left that out, the linear regression is bent away from that. When we include that data point, the fit is bent towards the data point. And then these are the denorm observation likelihoods from those two models visualized. And then this is just showing how I created those residuals. So the main residual, the standard one, is just the observed minus the fitted values. And the leave one out one, we could calculate it ourselves, but we can use some trickery within the LU package to do that for us. So that's what's happening here. We'll talk about that trickery and come back to it. This is plotting out what I just created. So we've got, again, the leave one out residuals are always larger than the fully fitted residuals because the open circles are further away from the zero line. That's all that's showing. And if we wanted to calculate, say, the R squared for that, we can do that. First, I'm just going to look at the standard deviation to show that standard deviation is wider for those open circles for the leave one out residuals. And R squared can be calculated as 1 minus the ratio of the 1 minus the variance from the residuals divided by the variance of the response itself. So we can calculate the R squared, and we can see that the R squared on the fitted data is 0.74, so it's explaining 74% of the variance of the fitted data, but only 67% of the leave one out data. So R squared is going to be higher on the fitted data than the leave one out data. So now we're going to calculate those ELPDs that we talked about. So we can grab those log likelihoods, and these are those things that we were calculating the generated quantities ourselves. There's a function to grab those from an rstan-arm model, log like. So this has created the matrix of those log likelihoods. We'll do this ourselves in R right after this. We're sort of doing it in the more efficient, briefer code version first before we do it ourselves in R. So I'm not going to spend too much time on this because I think it'll make more sense when we actually do it ourselves. But this is doing the sum of those in a computationally efficient way in log space. And then we're going to calculate the expectation for each observation. So here we're going to do it by hand here. So that was the sort of the fast way to do it. Now we're going to do it by hand. This I'm going to focus on because this I think is what's important to understand what's going on. So if we're going to create an empty matrix of NAs by default, and it's going to have the number of rows, the number of simulations, and the number of columns of the number of observations that we have. So I think it's 20 in this case. And then we're going to iterate through our posterior, and we're going to iterate through the MCMC samples, and we're going to iterate through our observations. And we're going to create our predicted values, which we're going to call y hat. Hat is often used for expected values. So these are our expected values of y. All I'm doing is adding our intercept plus our slope from our posterior times the corresponding predictor, x. So now I have filled this matrix here, which is one row for each MCMC sample, one column for each observation. These are our expected observations. Simple enough so far. Now we need to grab those point-wise log likelihoods, those things that we calculated in the generated quantities before. To do that, we can just iterate through those expected values we just created for each MCMC sample, for each observation, and with our observation error standard deviation, which is the third column in our posterior matrix, and we're going to record them in log space. So now we're calculating those lengths of those horizontal red lines in the slides that I showed. So now we have a matrix, and these are the point-wise log likelihoods, as we call them, for each MCMC sample and each observation. Now we take the average density for each data point across MCMC samples, and this is the critical part that's easy to make a mistake on. You average the likelihood, not the log likelihood. So the sort of naive way to do that would be to exponentiate our log likelihoods, and then for this column-wise, apply it. So for each observation, take the mean, and then take the log of that. So this is that slide where we had the histogram and we had the vertical y lines, and we're taking those means and then putting them back in log space. So that was the sort of naive way to do it. It works just fine here because we have a very simple model that's fit very well. This is the computationally safer way to do that, where we don't leave log space. So this does it all in log space, which is safer. This does the summation in log space, and then you subtract is the same as dividing in natural space, subtracting in log space. So we've ended up with the log of the average of the likelihoods. And to prove that what we've done is the same, I'm just going to plot that to show that our like very coded out naive way we've done it in R fully matches what we got from the calculations we did before. I've just plotted them against each other and put a 0 to 1 line through them, so they are the same. Now, if we want to calculate our ELPD, all we need to do is sum those log predictive densities. And indeed, what we've done gives us negative 26.8 rounded to one decimal place, which is exactly the same as the one coming out of the LU package. So we've recreated the expected log predictive density, sometimes called the log score at this point, because we haven't actually done this on left out data. We've done it on the full data set, on the fitted data set. And I got that by passing it in to the ELPD function with the log-like function to the fit. So far I've just proved that our way of doing it is the same. That's all that's happening behind it. So what we now want to do is extend this to the leave one out context. And so of course we can do it all in one line of code with the LU function. And that gives us our ELPD for leave one out data. We want to try and get to this negative 29.5. We're just going to save those point-wise leave one out values because we're going to use those later. Okay, so if we wanted to do that ourselves in the naive way of actually refitting the model over and over and over, which we can do here because it's a pretty simple example, that's what I'm going to show here. So I'm just going to iterate over n, which is the 20 observations. I am going to take out each observation into this dot. I'm going to fit to this dot, so that's everything except for my data point of interest. I am then going to grab the MCMC draws themselves, and I'm going to do what I did above, which is just create an expectation matrix, create a pointwise log likelihood matrix or vector, and I'm going to do that calculation here, and then I'm going to do that computationally dangerous, the mean of the likelihoods and the log of it, and the sum of those will be our ELPD, leave one out, calculated literally by leaving out each data point. So that's going to iterate through, wait for our 20 data points. Okay, and then if we look at the sum of those, we get negative 29.51, and then the sum of them from the approximation is virtually identical. There's a little bit of variability in the MCMC one because this is a stochastic MCMC algorithm. But to 3 decimal places, they are identical. But one forced us to fit our model 20 times. The other one, we didn't have to refit our model at all. So we can compare our pointwise log scores, which is just the basic fitted ELPD, to our ELPD leave one out. And there we go. So our log predictive densities are lower for the leave one out version, as we would expect. It's harder to predict the left out data. The regression lines are not bent towards the data itself. And if we wanted to calculate LUIC, all we need to do is take -2 times the sum of those. So that gives us 59, 59. Again, the same answer. Okay, so here's an example, and this is from the Regression and Other Stories textbook by Gelman and Hill. This is an extension of the original Gelman and Hill 2007 black and orange book on multi-level modeling. I forget exactly the title, but this is from Regression and Other Stories, and it is a data set about child IQ scores, trying to predict child IQ scores. You've got mom IQ scores, several other covariates, such as whether the mom finished high school. It's from the National Longitudinal Survey of Youth in the States. So if we look at kid IQ, we've got the kid IQ score, mom high school, mom IQ. I think that's all we're going to work with in this example. So we can fit a simple linear regression of kid score as a function of 0 or 1. Did the mom go to high school, finish high school, and then the mom IQ score. Look at our model. And so there's an effect of both, whether the mom finished high school as a effect of 5.9 with a standard deviation or standard error of 2.2, and the effect of per unit of mom IQ is also substantially different from 0. We can compute the R squared and the leave one out R squared manually if we want. So I'm going to take the fitted value, the in-sample R squared, and the out-of-sample residuals for both. Calculate the R squared by 1 minus the variance of those residuals divided by the variance of the response. You'll notice that, So it's higher for the in-sample one, as we've seen before. It's harder to explain the variance of left-out data points, so the R-squared has gone down. So here's the point that I really wanted to get to, which is looking at understanding how different the ELPD values are and if they're meaningful or not when you add predictors to your model. So there's this slick code here that is from the textbook where I'm just going to add, if we look at kid IQR, I have quickly created 5 variables called noise 1 to 5. And we can actually access those through this trickery with the, because they're like an array in an object here for noise, this is all just a fast way to add 5 noisy variables that are completely random into a linear regression is the point here. And I'm going to refit that model. So now we've added 5 variables that we know are gibberish, and we've tried to estimate their effect. So let's look back at our R-squareds. So we'll calculate their residuals, and then the R-squared and the R-squared. So if we look back to the original R-squareds, so let's keep track of these. This is with gibberish predictors added in, and this is before. So our R-squared on the in-sample data has gone up, even though we've just added 5 random predictors into our model. Our R-squared is going to get better because we've added more predictors. But our R-squared of left-out data has decreased. So adding those 5 noisy predictors has decreased our ability to explain the variance of left-out data points. So we've reduced the predictive capacity of our model. But if we just looked at R-squared on our fitted data as we normally do, it's going to look better and better and better as we add more noise to our model. So that's the whole reason why we're doing this leave one out exercise in the first place. And if we were to look at ELPD of our initial model and our model that has our additional 5 gibberish predictors, and we can look at the difference, we'll see that the expected log predictive density has gotten better, but it's gone down. It's gone down by 2.3, and we talked about how the expected loss of the leave one out ELPD is 0.5 per random predictor variable. And that works out to basically, almost exactly the negative 2.5. So higher ELPD is good. We have gotten worse in our leave one out ELPD by roughly 2.5 units because we've added 5 noise predictors. So you can use that to scale your expectations. If you add a predictor to your model and the leave one out ELPD gets worse by 0.5 units, your predictor you added is as good as noise. And if we had calculated that, we're not showing it here, but if we had calculated that on the in-sample, so the log score version, it would have got better by 0.5 units per noise predictor that we added. So in a more realistic scenario, we might add an actual predictor to our model. So let's try one where we only have maternal high school indicator. We've left out the mom IQ, call that fit1, and then we will compare them. So here we can see that our original fit3 that included the mother's IQ is substantially higher. So we've got one parameter difference with a difference of almost 39 units of the leave one out ELPD and a standard error on that difference that is not going to include 0. If we add or subtract 2 times that, that's the 95% credible interval on this difference, roughly. So we have a substantial difference both in magnitude and in our significance with our standard error. So we would conclude that the model with the mother's IQ in it is a substantially more parsimonious model. So one thing we can do from that is to pull out those pointwise, so the observation by observation, left out residuals. We can do that by grabbing them from the object that we get out of the LU function using this syntax. So we're grabbing the ELPD pointwise. Subtract one from the other, and this can be a useful way at looking at which data points are better predicted by one model than the other. So in this plot here, the observations that are above the 0 line favor model 3, which is the one that had the mother's IQ in it, and the ones that are below favor the simpler model. So we can see in general, these dots are above 0. That's because we know in general it was a better out-of-sample predictive model. But there could be some things, if we were to pull out the identifiers for these individual data points, we might learn something. Maybe there's some reason we can think of why these data points were much better predicted by this model or this model, and adjust our model or think about what other covariates might need to be in the model to improve that. So that's really the extent of the model comparison that I wanted to show with ELPD and LU-IC. But mostly from my own interest at the time, and I just thought I'll leave this here so that you can look at it if you'd like. I wanted to work through how that approximation works within the LU package. So what we're going to do is just do that resampling ourselves to prove that nothing fancy is happening. So to do that, remember that we had these expectations for each data point. So this is, each row is an MCMC sample, each column is an observation in a matrix that we're calling y hat. And then recall that we can calculate the log density for each observation. So this is the pointwise log likelihood. We've done this over and over now. So we've got I hope I ran that right. Let's run this. Numbers. And now we want to weight the MC samples by the weights of 1 over the density, or equivalently 1 over exp of the log density. Because we're keeping track of them in log space, we just need to exponentiate them. So this is just the sample reweighting that I talked about. The key part here, the fancy part, is that we're calculating the weights as 1 over the likelihoods. And then when we sample, we just pass those weights as probability arguments. We did something similar on the very first day when we sampled from our grid search approach to come up with samples from our posterior. That's the importance sampling, as it's called here. And so if we run that, remember we're aiming for negative 29.5, we get negative 29.5. So that is all that is happening inside the leave one out. The only addition is that because some of these likelihoods get really, really tiny, it fits a Pareto distribution smoother to it first before it calculates, as opposed to using the raw weights themselves. And we don't need to do that here because it's a model that fits really well. There's no data points that are poorly fit. But that is important to know because in the output, here it says all the Pareto K estimates, so that's the parameter in the Pareto distribution, are good using this criteria of K of less than 0.7. So you may get warnings that there are some data points that are not well approximated by the Pareto, often because they are extremely unlikely observations that are very poorly predicted. And so what you'll have to do, and you can Google this, there's lots of examples of this, but you just need to, you may want to refit those specific observations to calculate the log likelihood for those calculations exactly as opposed to using the approximation, and then they can be combined back in. So just be aware that if you get warnings about the paired OK, that means that some of the data points weren't fit well, and if they're really far off, you're going to want to deal with that. And it means that there are some outliers in your data, so you might want to think about your model and whether or not you can better fit those outliers in your data. So some resources with respect to what I've talked about. This Pareto smooth importance sampling approach is in this paper, this preprint. And the sort of main paper that talks about leaving out cross-validation as part of originally WAIC, which is another information criteria, similar, it's kind of moved into this ELPD LUIC. But this is one of the sort of foundational papers on this. And then this is getting into the Pareto smooth importance sampling that we've talked about here. The LU package itself has extensive documentation, and they have this glossary page which defines some of the things that we've been talking about with ELPD, the standard error on the ELPD, and talks about those Pareto K estimates and what they mean and what you can do about it if you have bad K values in some of your Pareto smoothing. So if a lot of that went over your head, that's absolutely fine. This is here for you if you want to try and wrap your head around to really understand what's happening. The important part is just keeping track of the fact that there's a reason why we want to evaluate models on left out data. That leave one out is sort of the limit of this K-fold cross-validation. And there are computational trickery we can do to get at these leave one out information criteria that are efficient, that we can get out of our Bayesian models by just keeping track of those pointwise log likelihoods, and that judging how good our models are should probably be done on left out data, and that how good a model is at predicting left out data is a useful way of comparing models, and we can do that using the LU package by looking at these expected log predictive densities between models, where higher is better, and we have some way of judging the scale of those differences based on our understanding of how pure noise predictors will affect that ELPD value. So this is useful if we want to do any kind of model comparison. Basically is what this is all about. Decisions about whether or not to include certain variables or whether or not certain models are better at predicting out of sample data.